Okay, today I'm going to show you a tutorial on Solidworks Simulation on how to do the thruster transient analysis that we were talking about for the project, the design project. And so this is what it's going to look like. But in case you don't know how to use Solidworks, I'm going to go ahead and start from the beginning. So let's go ahead and create our model. So if you have, let me go ahead and save this. If you go into SolidWorks, what you want to do is you want to create two parts. If you remember, there was two cylinders associated with this. I had a hard time trying to analyze a single part, so we're going to create an assembly made of two individual parts in SolidWorks. So the way you do that is you go ahead and create a part. File, New. So you go to File, New. It's going to ask you, I want to do a part. So I'll go ahead and hit OK. And these two parts, we're going to put them into an assembly, and that's what we're going to analyze. So SolidWorks creates an open blank page. And what we're going to do is first you need to start, I usually start on the front plane. So you go on the left hand spine here and click on front plane. That's where we want to start our drawing for our larger cylinder. So once I select front plane, I go in and create a sketch. So I go to the next tab, hit sketch. And now I can create my cylinder. So I go ahead and create a circle. And I'm going to start at the origin here. So I clicked on circle. Doesn't matter where I can start up here. Doesn't matter, but I'm just going to go ahead and center it on the. And the unit should be in inches. So I'm not really sure. So I'm just going to arbitrarily pick a cylinder like that. And well, I'm going to go ahead and create. I want to see what the dimensions are. So what I did is I on the sketch tool, there's a smart dimension. I click that, click it on the circle, and you can see, I think this is millimeters actually. So instead of going and changing to inches, I'm just going to convert to inches. I'm not really sure how many millimeters. I know how much in inches I want this, but I'm not sure how much in millimeters. So I know it's about the outer diameter. I'm going to just right now about. Going to start with about a 2.8 millimeter. I'm sorry, 2.8 inch diameter outer cylinder. So I'm going to say 2.8, and since it's in millimeters, I'm going to say divided by 25.4 millimeters in an inch, and that should convert it to inch. Hold on a second. This is already in millimeters, so it's 2.8 inches. So is it 2.8 times 25.4? Yeah. So that gives me about 71 millimeters. That's right. So, and then I'm going to create a center core in there. And that one, again, you have to go into the project description, try to pull out your dimensions, but I'm just going to go ahead and put 2.2 inches here. So I'm going to go and right now it's saying 41. Let's see how, so I want to do 2.2 inches, 2.2 inches. So because this is in millimeters, I have to multiply by 25.4 millimeters in an inch to convert it to millimeters. So that's it. So it turns out we're doing a 71 millimeter and a 55.8 millimeter or 55.9 millimeter dimension cylinder. So now we want to go ahead and, right now this is just a 2D sketch. We want to go ahead and extrude this and create a 3-dimension part. So we go ahead and hit features on the tabs up here, extrude. And we want to extrude to about 4.3 inches. So again, this is in millimeters. Let's see what that is in. So it's 4.3 here on the dimensions times 25.4 gives us, so that 4.3 inches is roughly 109.2 millimeters. And we hit, that's what we want. We say OK. This isn't that important here, but I'm gonna, well, let's just leave it for now. So here's our first cylinder, and we're done. So I want to go ahead and save this part. So I'll hit save. Now it's asking me what to save it as. So right now it's pointing to my MAE 431 directory. We'll go ahead. I'm going to create a folder there and just say new folder in that directory, and I'm going to call the folder practice 1, and open it or double click it, and I'll save this as part 1. That's fine. That's the default name. And now I'm going to create a second part. So I'll go ahead and say new, go to File, New, create a part. Okay. And again, just to stay consistent, I click on the front plane here on the left-hand side spine and start my sketch there. So hit that front plane and go to the Sketch tablet and hit Sketch tab, and hit circle and start at the same center of origin. And now for this one, I want to go, the inner diameter of the last part was 2.2 inches. I want to do this outer diameter of this part as 2 inches. So there's going to be a 0.2 inch overlap. So I'm going to start with this being 2 inches. So for that, I just arbitrarily just dragged it and stopped. Now I'm going to give it a dimension by clicking Smart Dimension, clicking the edge, clicking it down, and then just say 2 inches, right? So that's 2, because this is in millimeters, I have to convert to millimeters, so it's 2 times 25.4 millimeters per inch, and that's roughly 50.8 millimeters. That's my outer diameter. Now I want to put an inner diameter in here as well, and for that, I'm going to arbitrarily select 1.7 inches. So I'm going to click my Smart Dimension, click on the edge, and then I said 1.7 times 25.4. And so it's a much thinner part than the other one, and that's fine. We'll go ahead and do that. So I can hit escape, that's fine. So it's my 2D drawn part. I want to go ahead and create a 3D extrusion. So from Sketch tab, I go to Features, select Extrude Boss Base, just like I did the last part. And I was defaulted to a 10 millimeter extrusion, but I want to go, I don't know in millimeters, but it's 5.2 inches I want to go. So I'm going to say 5.2 times 25.4 millimeters in an inch to convert it to millimeters. That's 132, roughly 132 millimeters. And I'll just hit yes, go ahead. Now this is a symmetric part. There's no, back or front. Doesn't really matter. I guess you can say where you started the sketch, that might be the back. And you can just, by selecting the front plane, that shows you where you started the sketch relative to the plane. Now I have 2 parts, but I'm going to go ahead and save this part. So I click Save, and it's going to go to the same directory as the previous part, and it's part 2, and that's fine. Alright, so I have 2 parts now, and what I want to do is create an assembly of the 2 pieces. So for that, I have to create a new, something new here. Go to File, New, but this time an assembly. That means it's multiple parts. Click that and then click OK. And what it's going to do, it's going to look at the parts that are open, and it's going to allow you to select one to put in. So I'll click with the first part here, and as I do this, it kind of drags it into place. I'm not even clicking the mouse, but it's just kind of dragging it as my mouse travels. It doesn't matter where you place it, just click on the screen, and there you go. Now for the next part that you want to bring in, you want to weld it onto this side or to each side. They're symmetric, so it doesn't matter. So for that, what you want to do is you want to go to, you want to look at the other part and just drag it into this window. So for that, you go to the SolidWorks menu up here, File, and actually go to Window, and you want to do a tile window. So tile horizontal. And now this shows you all the parts that are open. Ignore this top one here. I had that's just from a previous, so I'm going to go ahead and just X that out. I don't want to save it. And so let me go ahead and do window tile horizontal to kind of fit everything into place. And so this is the part, that's my thick outer large part, and I want to bring the thinner one and connect it here. Right now it looks a little bit out of scale, but if I go to my feature tree here in SolidWorks and I click on part 2, I can just click on it and drag it and just, let's see, Um, actually, these are, oh, I made a mistake. I went ahead and I deleted the assembly that I just created. So hit new assembly. I really apologize about that. And just click that first part and drag it in. And I was right. I was wrong. Actually, I should go ahead and go back to tile horizontal. This is where we stopped off. So this is the new assembly up here. Now what I want to do is drag, it already has part 1 inside of it. What I want to do is grab part 2 and drag it here. So that's what I want to do. So sorry. Alright, so I don't like working in this small window, so I'm going to just maximize it. And what I want to do is I want to mate these parts here. Basically what I want to do is, I'm in assembly mode here. I just move my component and want to put it somewhere right here. Now this is, just kind of just, and then I kind of want to have them touch or weld. I'm going to imagine that they're welded together. So for that, I'm going to hit escape. I want to do this function here under assembly tab inside your assembly 2. You go and hit this paperclip, which is the mating feature. It allows you to go ahead and connect parts. So I'm going to just click the outer cylinder of the big one, click the outer cylinder of the little one. It automatically brings them together. Now it does a concentric mate, which you can see there's this overlap here. You could choose to overlap it like that. That's fine. In fact, I might just leave that, or if you don't like that, you can go ahead and accept the fact that they're concentrically mated, but they're not, well, you're not done yet with the assembly. So if I went ahead and just hit the green arrow to say, okay, we like that, we're not really 100% done yet. We still have this thing kind of, can go right through it. So what we want to do is, I'm going to go ahead and rotate the view here. The way I rotate my view, I wish I could show you, but I'm clicking the little scroll wheel on my mouse, click it down, and then it gives me that ability to, if you don't have if you're not using a mouse, you could go to File, View, Modify, Rotate, and that does the same thing. Now I'm holding the left click on my mouse. But I mean, if you had like a scroll pad on your laptop or something, this is what you might want to do, because you probably don't have a scroll wheel. Again, that's how you access those. So you go to the SolidWorks menu bar, go to File. Wow, I have to hit escape there. Go to File. So, well, I showed you right there. So right now we're inside the. Let me escape out of this. We're going to go ahead and just weld these two pieces together. So to do that, I'm going to go ahead and pan the object. I'm going to hit Mate. Now I got to select two surfaces. I'm going to select the surface, that one of the smaller cylinder, and this one of the larger. Now there's a problem here. You see they're not touching. This is kind of surprising. I thought, oh, I know why. Because this cylinder is 2 inches on the outer diameter. That's fine. So I'm going to click OK. Right now they're just floating in air, this cylinder relative to the bigger one. So I'll click that green arrow on the mate. So what I want to do is I want to make this cylinder, either this one, this inner diameter of the big one smaller so it overlaps, or I want to make this diameter of the smaller one larger so there's an overlap. What I'm going to do is I'm just going to create just change the inner diameter there. So for that, I don't have to close out. What I do is a lot of things here work on as right click. So I just want to edit this big part. So what I'm going to do is, and you may not, okay. So I'm going to right click, and then there's this feature here that says edit part. Remember, we're in an assembly right now. You can't edit parts. You can only bring them together. But you can't do anything to the part unless you go ahead and tell the computer, I want to exit out of the assembly and edit. So you click this again. Let's do this again. So I'm going to click on the surface of the part I want to edit, and then I right click. And I hit this edit part symbol. And it says I need to save my assembly, and that's fine. I'll save it as assembly 1. inside my folder. Just hit save. Now what it does is it makes the part that you're not editing transparent. And now I can go ahead and edit this just as if I had this open in the window where I created it. And now what I want to do is, so this is the blued out, there's two parts that make up this assembly. The one that's in blue is the one that's currently edited. I'm going to click the open arrow there. And the boss, if you guys remember when I extruded that two-dimensional drawing, there is if I click the arrow of this boss, that's the boss that I use, the extrusion. So it's going to give me a sketch, and the sketch where I actually created that extrusion. So I'm going to right click the sketch and say edit sketch. And if you remember, I made that, I meant to make it 2.2 inches, but I'm going to have to make it less. So right now let's just go ahead and it's 55 millimeters. Let's just stay in, it doesn't matter what, I'm going to say 40. I want to do a 40 millimeter. And now I think there's going to be an overlap. So I hit 40, hit return. And now what I do is I go to exit sketch. And you can see this overlap. The part's transparent, but you see this band here shows where now there's an overlap between the big cylinder and the little cylinder, the thinner cylinder. So now I go ahead and go to the top left and edit where it says edit component. I want to just click that to exit out. There was also another symbol down here that showed you how to edit that, how to get out of that edit part. Now I'm back in my assembly, and there's an overlap. You can see here, you can see that ring in there. There's that overlap. So which is, if there's no overlap, if they were just floating in space, I wouldn't be able to transfer any temperature. Okay, so now I'm good. Now I got a part, and I'm ready to do, so I'll go ahead and save. I'll go up to the top left here, hit save, and save all. I want to save all my parts. I want to save this assembly. And now I'm going to go ahead and do a simulation. So for that, I go and hit the simulation tab. This puts me into Solidworks Simulation. New study, I click the little arrow under there, and I do want to do a new study. I don't want a simulation advisor. I just want to go ahead and create a new study. And these are the different types of simulations that we can do. We want to do a thermal. Though I think I have to figure out how to do a fluidics analysis, because actually, if this part was very complicated, surprisingly, a fluidics analysis or a Flowworks would be much more efficient. But right now, we're just going to click thermal, and the default name is thermal 1. That's fine. So now you have a tab here at the bottom left that shows we're inside the simulation mode. Now the first thing you want to do is you want to where it says parts, you just follow the direction here. You're going to go from top to bottom. So actually, why don't we go to the very top where it says thermal 1. We're going to make sure we do a transient. Right now, SolidWorks will do a steady state as the default. But we don't want a steady state. We want to do a transient. We want to see temperature versus time. So we go ahead, like I said in the class, right-clicking symbols a lot of times get you where you want to go. So you right-click here where it says thermal 1, right-click, and what we want to do is go to properties. And we want to change it from steady state to transient. At this point, we want to go ahead and do the time that we want to simulate to. Remember, we're trying to get. I want to know how long it takes to cool down from 220 degrees Celsius to 20 degrees Celsius. And I told you that the satellite pass or the Dawn spacecraft pass that we have where we communicate with it it's a 4-hour window. So we don't want the analysis to go larger than 4 hours. We want to go. So right now I'm just going to say 10,000 seconds is kind of good. That's pretty close to 4 hours. So that's 10,000 seconds. And because it's asking you for it in seconds. And then I don't want to do 0.1 increments. That would be 100,000 calculations, and your computer may not be able to handle it. We don't want that kind of detail. So I'm going to put 1,000. So it's basically going to do 10 iterations. Now you might want to do better than that. This is just so I can do a quick analysis while, and not run this video for 10 minutes, and so 10,000 total time, the total time is 10,000 seconds with 1,000 increments means there's going to be 10 iterations. And that's it. We do that and we hit OK. And now we're in transient mode. Now the next thing you want to do is go to parts here. You click the arrow to open that the parts, and you have the two parts. You have the big one and the little one, or the thick one and the thinner one. And so you need to select a material. So we're going to select this. I don't know. I think I mentioned that it's okay to just do select aluminum for both. So what you want to do, if you're going to select the same material for both, you right click the well, actually you can click one part, shift, and click the other part to kind of highlight both, and then just right click and apply materials. Now SolidWorks has a database, and it's defaulting a material for alloy steel, but for some reason it doesn't really recognize it unless you select it. If you tried running this, even though it's telling you it's selecting alloy steel, the analysis say you didn't select a material. So I'm going to go to aluminum alloys. So there's a SolidWorks materials and there's the DIN materials, and I think it's kind of the same. But just go ahead and go SolidWorks materials, click that, go to aluminum alloys, and it doesn't really matter. From a thermal standpoint, they all pretty much have the same thermal conductivity. These alloys and tempers are more from a strength standpoint, but usually if you want to get used to a very common alloy, it's 6061 T6. It's another word for it is automotive aluminum, and we use this for all our spacecraft. This is kind of the main one. There's for if you want larger strength, and there's other alloys, but 6061 T6 is a good one. So you click that and hit apply, and you close. So now what it did is you could see it, and it gave you a little check that you selected material. Okay, you don't need to have a component contact. If you right click, if you go ahead and go to components contacts, it's going to assume that they're bonded together. Some programs will assume that they're not touching, but SolidWorks always assumes that these things are welded. And that's what we want. We want a weldment. We want to make sure this isn't glued. If this was glued, then you'll have to put a connection in here that says, well, there's actually a glue there, and then you have to come up with a contact thermal resistance for that glue. If you guys remember from one of our chapters, I don't know if it was chapter 2 or 3 where we might have been 3 where we come up with contact resistances. But right now we're just going to assume they're bonded. So close that. Now we go to thermal loads, and you're going to have to right click on thermal load, and we want to do a temperature. Remember what I said? You want to assume that that this thing starts off at 220 degrees. This is what we call the cap bed. Now, I don't feel comfortable selecting a surface and saying that temperature is initially 220. I'm sure that's fine. I'd like to select the whole extrusion. So for that, you got to go and you got to go to the feature manager tree from when you built the model. And for that, you have to go to this little bullet up here at the very top, and you can split this window. So you grab that bullet, split it down like that. Now you got your feature manager tree here, and you got your simulation window. So I'm going to select not part 1, but part 2. This one, you can see by hovering over it, it's already giving us a highlight. So I click that whole extrusion, and now I'm going to put the window back up, and it's telling us it's setting us 0 degree Kelvin. That's probably okay, but I feel uncomfortable. No, I'm sorry. Not for the initial temperature. It's supposed to be 220 Celsius. So first I got to change it from Kelvin to Celsius, and then it converted 0 Kelvin to, now it's minus 273.15 Celsius. I want 220. That's my initial temperature. It's asking if I want to use the time curve. So this is initial temperature. You got to make sure you click this up here, initial temperature, or else it'll hold it at 220 for the whole analysis, and that's not what we want. We want it to start off at 220, and then we want it to cool down. So it's an initial temperature. So hit OK. And the other boundary condition we want to do, I think we set back here where it's connected to the spacecraft. I think we said 10 degrees. We want to hold that at 10 degrees at all times. So I selected that surface. I go to thermal loads, right click, temperature. I just make sure it's not initial temperature. This is a constant temperature. So we leave it at temperature. We change it to Celsius and we say 20. And we hit OK. And you can see it gives you some arrows there indicating that you have a boundary condition there. You didn't get the temperature boundary conditions for the initial temperature because it's not a boundary condition. That's an initial temperature. It doesn't have arrows. So this just means it's always on. It's always at 10 degrees here, regardless of how this thing, and that's fine. That's what we want. And the spacecraft actually tries to hold this at about 10 degrees. So then, now we don't have, now we have, we're not done yet. We need to do the actual, environment, right? What's going on? We have radiation, right? So we have to go ahead and right-click thermal loads. Now we go to radiation. And I'm going to say, well, both surfaces are actually radiating to space. So I click both surfaces. You can click the surface here, but it's so small it doesn't matter. And now it automatically defaults to surface to ambient radiation. That's what we learned so far in class. This cylinder is going to see cold space, and cold space is not a surface. It's just basically an environment. It's what we, or an ambient, but it's really like an environment that doesn't change. It's always at a certain temperature. So we leave that. Surface to surface would be if you had another part this was inside of another part, and you wanted to see radiation exchange, and that's not what we're looking for. So we leave it like that. Now we're gonna need to put a temperature of the ambient, and that would be, we'll leave this in Kelvin, okay, because this is cold space. And what I do is I'm gonna put 80 Kelvin because space is actually closer to 0 Kelvin. You can put 0. Some people put 3 Kelvin as more of a representation of cold space. 80 Kelvin is what we would do if we put this in a environmental chamber and want to recreate the coldness of space. We actually have a chamber that we run liquid nitrogen in, and the walls of the shroud inside this chamber are pretty close to 80 Kelvin. But that's, if you do the math, it's pretty close to 0 Kelvin. I mean, the effects is very small. The difference between 80 Kelvin and 0 Kelvin when you do the temperature analysis is pretty small. So we'll leave it at 80 Kelvin, but by all means, if you want to leave it at 0, you can go ahead. This is the emissivity, and I'm going to pick 0.6 emissivity. This means it's just, you can look at the properties of aluminum at the surface treatment and all that. This is a treated aluminum, and it's what we call chem film. You can look it up if you want to see what's a better emissivity, but I'm just picking 0.6. And this is the view factor. That means how much of this area is being exposed to space, to the environment, to the ambient. If you had some baffles blocking space, like if you had 50% of the view of this blue cylinder thing being obstructed, you would put 0.5. I'm just going to put 1, meaning there's no obstructions. 100% of the surface that I selected can see the ambient. So you can see, yeah, so it's a 1, so I'm going to go with that. That's my view factor, and then I'm good. So I hit like that, and I think I'm ready to go. Now I need a mesh, create the mesh. Remember, this is actually a finite element solver. In chapter 5, we talked about finite differences. This is not a finite difference program, but it's kind of on a similar concept, finite element. You right click mesh and just say create mesh. And it's going to give you a default setting, and just go with it. Say OK. And that's fine. You don't have to worry about, you just go ahead and hit the default for here. You could enrich it, you could refine it. If you had little holes or certain things that you needed to mesh that wouldn't mesh, you would go ahead and right click mesh and move that little bar to refine it, or pick a number of element dimension, but you don't have to do that for this. And now we're ready. Results is what happens when we solve this. So you're going to go to solve this now. You go to thermal 1, right click, and you're going to run it. It should solve pretty quick because we only have 10 steps. You see, we did a 10,000 second total time span with 1,000 second increments. Let's see how fast this solves. So it's getting there. It's actually taking a little longer than I thought, but just bear with me on this. So as it solves, yeah, there it goes. So this should be interesting. So total time elapsed was 37 seconds to solve here. And this looks about right. Let I'm actually a little surprised that there's such a large gradient here. Maybe because of but it doesn't matter. So right now the results, I don't like reading in Kelvin here. So what I do is I'm going to double click on this color bar here, and that opens up on the left hand side my settings. So I'm going to go ahead and go to definition. I'm going to change it. I don't like reading in Kelvin. I like the reading in Celsius. And this right now by default gives me the 10th. This is basically on at the 10,000 second mark, basically the end of the analysis. It shows me the temperature. And that's fine. So now I go to chart options, and I don't like scientific units. I like to see this in just normal floating with 2 decimal places. So I click that to 2, and I hit OK. And if you want, you could, that this is the coldest point right here, and it's saying that it actually dips down to 14.39 degrees C. So which is good. It tells us that we actually reached below 20 degrees. The whole thing reached below 20 degrees by 10,000 seconds, which is so. Let's go ahead and now let's do a graph, see the temperature versus time. For that, I'm going to go ahead and I got my results here. I'm going to right click, and I have to hit this thing called probe. It's because there's thousands of data points here, and I just want to pick one, and I want to map that, or I want to get a graph of that. So I click probe, and I'm going to pick. You can pick anywhere here. If you want, you can pick way out here, but this is the cat bed. I'm going to pick in the middle, right there. And so I click that. That's the 11,931 node, or node 11,931. And it's showing that it dips down to 15.07 degrees Celsius. Now I want to graph that versus time. So when I did the probing, it gives me this option here, report option. So I'm going to click the one right here with the little clock. And this is interesting. So I think what happened was, I don't even know what happened here. But I'm not sure why. I think I needed more data points here at the beginning, and it actually looks like it might have dipped down and warmed up. That doesn't make a lot of sense to me. It should be a nice continuous chart like that. But this is fine. It actually doesn't tell us a whole bunch. This tells us that, what does it tell us? It tells us that we reach, okay. So one thing's wrong here. I need a scale that gives me, I need something that tells me the temperature at 220. So let's go ahead, let's escape out of here. Let's see. I'm not sure here. So if I right click my thermal and I go to properties, it says I did a 10,000 second total time and a 1,000 second increment. So now so anyway, let's see. I'm going to double click on that. Then I'm going to right click probe, and I don't know why it's not giving me on my x-axis. It's not giving me the temperature up to 220. I'm worried that, let's go back, look at our initial conditions. I did say 220 there. So let me click on model at the bottom here to get exit out of this color chart and go back to thermal 1. And I did mention that this is initially at 220 degrees. Maybe I should have said the whole thing was 220 degrees. I don't think that's necessary though. And then I had a temperature, I think that meant to put 10 degrees on that one. So I'm going to right click, hit edit, 10 degrees. And then this is all the same. So I'm going to go ahead and rerun this. So I go right click on thermal and run. right. So as you know, it takes about 37 seconds. So meanwhile, okay, so I clicked. Here's my little thermometer there. I always have little surprises that pop up. Okay. So one thing I can do is I can actually save the data down, save it as a, you know what happened was probably, I think it started taking information at 1,000, let's see, let's go ahead and right click on temperature and hit probe. Click here, and I want to plot that as a function of time. I think the problem is that this thing transfers heat so well, there's a good overlap here, that what happened is that, you know, this is actually starts taking measure temperature at 1,000 seconds. I should have it take. So I might want to refine the analysis because I want to know what's happening here. This is basically telling me that by 1,000 seconds we're already. You can see this actually went down colder. By 1,000 seconds we were already at temperature. So we might need to refine the temperature increment. The other thing we can do is when you add parts here, the first part, this thick part, I'm going to change the material. It's actually, I believe it's more of a steel, like a stainless steel. So I'm going to go with stainless steel. See if this has, so I go to stainless steel ferritic, apply, close. And then the other thing is if I go to thermal loads, the radiation, double click on that. I don't think the emissivity is so high. For aluminum, I believe it's 0.2. And what else can I tell you? Let's go ahead and run that. Right click on and run. So I'm trying to give me, I think I might have made this too thermally well conducting, but you don't have to worry about it. You get what you get, right? Try to follow the project description as best as you can. Everything in there should be, there should be enough information there for you to select materials, select dimensions, and just run it and just report the temperature that you get. How long it takes to get to 20 degrees Celsius. What you might want to do is you might want to select another probe point. You might want to select a warmer, because you want to assure the whole thing reaches 20. So you might want to select the probe point that is on the warmer side instead of in the middle to get to assure that the whole cat bed is under 20 degrees. Or you might want to select a point out here somewhere, right? Even though I had mentioned it's the cat bed part, the part that's in here that you want to. Oh, the other thing is I'm not sure I have the right mass. So I forgot what the mass was off the top of my head. I'll show you how to measure mass on this thing. So let's go ahead and do the measurement of mass. So let's for that we'll have to go to click model at the bottom, and we'll go to the Solidworks menu here. You go to tools, and you can say evaluate and mass properties. And now it's telling me that this is 370.92 grams. I'm not sure if that's enough. I don't remember how many grams the other one was. So this is so 455 grams is a pound. So this is like about 3/4 pound or a little bit heavier for this whole system. If the way you change the mass is you can make it thicker, thinner, or you can actually fool around with the you can override mass properties here, and you can go ahead and select, for example, Or you can play around with the, yeah, you can override mask properties. Maybe it's better to go to what individual part and override the mask property of the part. So go and open the file of this part and change the, play around, or there's a bunch of different ways. You can make it, like I said, thicker, thinner to hit that mask. And so again, so let's go back to our simulation. Let's look at it. I'm going to go ahead and probe this. I'm going to select a probe point there, and I'm going to go ahead and map it. I think it's going to give me, so this actually, this doesn't make any sense. So let's try something else here. Let's go ahead and do the initial temperature. I'm going to right click and edit. I could have just double clicked it. I'm going to select that surface as well on this surface. Actually, no, let's delete that. I'm going to select the whole part. So part 1. So the whole thing starts off at 220. So put that back up, hit OK. And this will be the last run I do, I promise. So I'm going to go ahead and right click and hit run. So there's different ways of doing this. As I showed you in class, I had the bond line that I had here, you can see it a little bit, was really thin. So there was a very little connection between here and here. You can see this one, this is starting to get isothermal here. This is kind of all like uniform temperature versus this, because remember I changed the material to steel. So steel doesn't conduct as good as aluminum. And so it's now you see less of a temperature gradient. So the difference between here and here is just like maybe a degree now, where it was much larger. And there is a larger gradient between here and here because this is steel. And and actually we are holding this at 10. So let's see. Let's just run with this. I'm running out of battery. Okay, we're going to have to end this soon anyway. Brighten this thing back up. All right. Okay, this will be the last run. I got the analysis ready. You can right click, probe, click in the middle somewhere, and just map that out. All right, so now we got a better distribution, something I'm more comfortable with. So what you can actually you can screen capture this if you want, but a cleaner way of doing this is to save this as a CSV file. So file, save as, and then you would just graph response 1. I'm going to go ahead and hit return, save. Already exists, so yeah, replace it. And now I can go back into my directory and just pull out a Excel readable CSV file and just plot it out, and I can put in, axes. So what this tells us is that we hit 20 around here. So at the 4,600 mark, which is 3,600 seconds, is 1 hour. So it's a little bit over an hour. Okay. All right. Well, thank you for attending this class, and have a good tech week. And I'm going to have a good break myself, and we'll see you next time.